ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. What we're going to do today is we're going to take a look at what happens at the molecular level when our compounds dissolve, all right? And so there's a couple of different things that we're going to look at here. And the first would be what happens when covalent compounds dissolve. And then the second thing would be what happens when ionic compounds dissolve, because there's actually two different things that occur at the molecular level, and they are different enough that we want to distinguish and understand the difference in energies and the difference in what's going on so that we can understand why different things dissolve the way that they do, all right? So, first things first, what we want to understand is that substances with similar types of intermolecular forces will dissolve each other. And so that's a very important statement. I'm going to say it again. Substances with similar types of intermolecular forces will dissolve each other. And so what that means to us is that a polar solvent, right? A polar solvent will dissolve other polar or ionic solutes, all right? And so the term that comes to mind normally for students here is that the term like dessert, or the phrase like dissolves like. And what it really means is that polar solvents will dissolve either polar or ionic solutes. And then the opposite is also true here, that if I have a non-polar solvent, and so you're reaching back here thinking, oh, Lewis dot structures, polarity, electronegativity differences, ionics are always polar, and all that stuff is rushing back into your head. So non-polar solvents will dissolve non-polar solutes. All right, and so we're pretty familiar with the old example where I mix water with oil and they don't mix, right? One will not dissolve in the other. If I take a candle and I put it in water, it doesn't dissolve. But if I take sugar and put it in water, it does dissolve. So what's the difference? Why does that occur? And really, our idea here that substances with similar types of intermolecular forces will dissolve each other. All right, so polar solvents will dissolve polar ionic solvents, and then nonpolar solvents will dissolve nonpolar solvents. That's a huge thing that we're going to be focused on here today, ladies and gentlemen, so please make sure you got that down. All right? Okay, so the first thing that we're going to do is we're going to look at dissolving ionic compounds, and so this is going to be our first focus, is ionic. Now, when ionic compounds dissolve, sometimes you might refer to this as a dissolution, or even more appropriate would be to call it a dissociation, and we'll see why in just a second. But essentially, the dissolution describes the dissociation of ionic solutes when they dissolve in solvents. So again, dissolution is describing the dissociation of ionic solutes when they dissolve in a solvent. And so an example here, and this is the one that we saw in class, my NaCl. So I've got Na, and then I guess I could make Cl a different color. I'm not going to do that because it'll take too long. All right, so I've got Na, I've got Cl, Na, I've got Cl, and those are appropriate atomic radii, right? And so Cl, Na, the Cl, let me make that smaller there, and Na, Cl, and Na. So there, I've got solid NaCl, and so that's going to be the key there. I've got solid NaCl, so what happens when I drop this solid NaCl into water? Well, we get the reaction, we do NaCl going solid to NaCl aqueous. And remember, I want to use multi-directional arrows here to show that dynamic equilibrium that exists at a saturated solution. And so really what happens? So to explain fully what happens, we need to go back and revise and rack our brains to remember what the Lewis dot structure of water looks like. We need to remember the fact that water is a polar compound. It's got a partially negative end and a partially positive end because of the lone pairs on the central atom, as well as the electronegativity differences between the oxygen and the hydrogens. All right? And so what you're going to see here is I am going to start drawing water. I'm going to draw it as a Mickey Mouse, right? Where the large part's my oxygen, represents my negative part of the molecule, and the hydrogens are the ears there, and they're the partially positive side of the molecule, all right? And so what happens? Well, I get water, and what happens, my sodium ion, I know when I take NaCl, if I were to split this up, I would have Na plus and Cl minus, and so what happens is my negative side, my partially negative side of water, will actually interact here, right, with the sodium, and it pulls it off. It will pull a sodium completely off, and then the water will hydrate, or it will coat and surround the sodium, and it'll stabilize that charge, right? So notice the orientation on here. And so what happens if we get chlorine? Well, I get another water molecule that comes up, face the opposite direction, Cl minus, and so notice now I've got the positive, or the partially positive end of the water facing in with this negative molecule, and it gets a stabilization. So the water molecules will orient themselves in a way to stabilize the ions in solution. And so another big question here is, hey, will all of the salt dissolve? Well, no. The answer is no. No, it won't. All right? Remember, we go back to our saturated, unsaturated, supersaturated solution. There is a limit to the amount of solute that your solvent can stabilize. All right? And then the other question here is, does this require energy? Because a lot of you now are going and looking and saying, oh, well, wait a minute. I thought dissolving was a physical process. Mr. Dillon, you're talking about breaking Na and Cl apart. That's breaking a bond. That's breaking an ionic bond. And the answer is yes. And I'm going to have you recall something else, right? So Coulomb's law, right? Remember Coulomb's law. The force of attraction between two ions is equal to the magnitude of charge 1, magnitude of charge 2, divided by r squared. And this is equal to my lattice energy. And the lattice energy is the energy that it takes to remove these ions out of this crystalline structure, this crystalline lattice for ionic compounds. And so we have to understand that this interaction here between this water molecule and sodium has to be greater than the lattice energy for this substance to actually dissolve. And if it isn't, then this salt will not appreciably dissolve into solution. All right? And then the other thing that is really important to understand, this is why we use the term dissociation. Dissociation actually describes the separation of ions that occur when ionic compounds dissolve, right? And also, again, another big thing, ladies and gentlemen, this is also why we cannot describe all dissolving processes as physical changes, because if it's an ionic salt that is actually dissolving into water, then you are breaking an ionic bond, and by definition, when you break a bond, that is a chemical change. And so it's not as straightforward as we once thought that dissolving actually was. All right? So big takeaways here, ladies and gentlemen. Ionic compounds, when they dissolve, the water will actually have to pull the ions out of the solid. And then the water molecules will orient themselves around in such a way that they will be able to stabilize that charge in solution. And the amount of energy it takes to pull these ions off of the crystal lattice is actually very related to lattice energy, which is defined and described by Coulomb's law. All right? Okay. So now what we want to do is we want to take a look at covalent compounds. So what happens when a covalent compound dissolves? Well, it's similar in a way, but for covalent compounds, I am just going to draw singular large circles because a covalent compound, there's no ions in there. There's no metal, non-metal. And so I don't actually break bonds. And so the water molecules will still approach, right? It'll still have interaction between the molecules. I can still pull off one of the molecules, and then water, again, will orient itself in such a way, again, because we go back to the statement of where we started, that substances with similar intermolecular forces will simply dissolve each other. And so if I'm getting a covalent compound that dissolves in water, then it must be a polar covalent compound. And so this polarity, again, will be stabilized in solution through charges. And the big difference here is I don't have Coulomb's law, but I still do have some intermolecular forces between the solid particles of my covalent compound. And so again, I have to make sure, this does require energy to pull this off a lot of the times, ladies and gentlemen. I have to make sure that I actually can have enough energy. The interaction between the water molecule here and the covalent compound has to be greater than the interaction between these two compounds themselves, all right? And so the giant idea, right, here for covalent, the difference between covalent and ionic. We're not breaking bonds when we are dissolving covalent compounds. We're just overcoming the intermolecular forces between each of the covalent molecules in the solid. And then a super giant idea, all right, I'm going to write giant idea here, is that a solute, all right, and so I wrote it here, my solute solvent, and notice I changed this from what I originally wrote there. The solute solvent interaction has to be greater than the solute-solute interaction for something to actually dissolve. And so this is our supergiant idea. This explains a lot of what's going on with solubility and why some things will dissolve and some things will not dissolve. How much of it will dissolve is also related back to this and those intermolecular attractions that are going on between water or whatever your solvent happens to be. And so again, my solute-solvent interaction has to be greater than the solute-solute interaction for something to actually dissolve. All right? Okay, ladies and gentlemen, that was a lot. If you have any questions, get them down. I'll see you in tutorials for those. Otherwise, I will see you in class.